Okay, next we're going to take a look at some initial value problems, or an introduction into the most basic type of differential equations. Technically, whenever you have an equation that has a derivative in it and you're trying to solve for the original function, you're doing a differential equation. And those equations have initial conditions, which are ordered pairs usually, or just conditions that we can use to solve for the equation in a specific situation. So the initial conditions are going to allow us, to put more plainly, allow us to solve for c, so that we won't have a general antiderivative, we'll have the particular solution. They're going to allow us to solve for this exact c instead of having the solution generally. We're going to solve for our c's. Okay, so initial value problems will be similar. We're just going to go a couple steps further than what we've been doing in the general antiderivatives, getting particular solutions. So suppose f is such that it is the derivative of capital F, so capital F is the antiderivative. Find the particular equation for capital F, provided its derivative is little f equals cosine, and that this point lies on capital F. So since it is a particular equation, we want to know what the value of c is to make that equation go through this ordered pair. Okay, so we start with defining capital F to be, it's the antiderivative, so it's going to be the integral of little f. And so since I know that little f is cosine of x, I'm taking the antiderivative, or the integral of cosine of x dx, and I know that the integral of cosine of x is a positive sine of x plus c. Now, my goal is to find c. So now I know that capital F has this ordered pair. So if I use the ordered pair, so my ordered pair is pi halves comma 3. If I plug pi halves in for x and 3 in for f, I'm going to be able to solve for c. So 3 is going to be equal to sine of pi halves plus c. So sine of pi halves is 1. So 3 equals 1 plus c. So 2 is equal to c. And so our particular solution for f is sine of x plus 2. Okay. Now, in the graph shown right here, this is a sine graph, but it's not sine x plus 2, it's sine x plus 0. And so if I wanted this actual graph, it would be the one parallel. Forgive my drawing skills here. The one like this. There. So this is the specific graph f of x, where again we have that family of parallel functions. And so we have many, many possibilities that don't go through that point that are general solutions, but we have the one particular solution that goes to the ordered pair that we were asked to go through, and that is this function. All right. So let's take a look at another initial value problem. Okay. This one gives me a second derivative, and so I have two initial conditions. One of them is for the derivative, and one of them is for the original function. So we're going to solve two initial value problems here. So first, I know that the derivative is going to be the integral of the second derivative. So I'm going to go up one layer here. So we're going to take the integral of 12x plus e to the x dx to find the first derivative. If I was given the second derivative, I can integrate once to get the first derivative. So I've got 12, x to the 1 plus 1 is 2, divided by 2, derivative, antiderivative of e to the x is e to the x, plus our c. I can simplify that as 6 plus e to the x plus c. 6x squared, sorry. I got excited about reducing that fraction, I forgot my x's. Okay, now we know that our initial condition for the first derivative is that if I plug 0 in, I get 2. So 2 is the y value, equals 6 times 0 squared plus e to the 0 plus c. E to the 0 is 1, so 2 equals 1 plus c, so c is 1. Okay, c is 1. C is 1. So that means that our particular solution for f prime of x is 6x squared plus e to the x plus 1. Okay, halfway there, we get to do it again. Now we want to find the particular solution for f. We know that f of x is going to be the antiderivative, or the integral, of f prime of x dx. So it's the integral of 6x squared plus e to the x plus 1 dx. So 6 times x second, raise it one more power, so 2 plus 1 is 3, divide by new power, divide by 3. E to the x integrates to e to the x, 1 integrates to 1x, or x, plus a new constant c, not to be confused with the old constant c. It's not necessary to subscript them c1, c2, because there's no more c in this equation, so I'm just going to call it c again. Okay, and we're going to find the new c. Now we're going to use the other initial condition, the one for f. When I plug 0 in, I get -5. So -5 is the y value, equals, I forgot to reduce, but that's okay. This is 2 times 0 cubed plus e to the 0 plus 0 plus c. Again, 0, e to the 0 is 1, 0. So -5 equals 1 plus c. So I'm going to get -6 for c. And so we can finish off our initial value problem here with f of x equals 2, I'm reducing that now, x cubed plus e to the x plus x minus 6. And now we have our final answer to this initial value problem. Okay, let's take a look at the next page. We're going to talk about motion. Okay. So what good is it to find antiderivatives, especially if they aren't unique results? Well, remember that for some specific context, we already know the relationship behind some functions and their derivatives. Okay, so blank is rate of change of position, so that would be velocity. Velocity is rate of change of position, so it makes sense that position is going to be the antiderivative of velocity. Also, blank is the rate of change of velocity, it's acceleration. And so velocity is going to be the antiderivative of acceleration. We use this diagram here to help us remember the relationship, a diagram of the relationship between acceleration, velocity, and position. Okay, so S of t is position, V of t is velocity, A is acceleration. And so if I'm differentiating, we would do derivatives down the list. So that would be our derivatives. And if we're integrating, we're going to integrate up the list. So if we integrate, we're going to integrate up from acceleration to velocity and up for velocity to position. Okay, so that kind of helps us figure out the relationship between these three things. Okay, so there are some physics tie-ins here as well. Momentum is equal to mass times velocity, force equals mass times acceleration. So we can continue derivatives of position. There's some wiki stuff, but like the derivative of acceleration is called jerk, the derivative of jerk is called jounce, and etc. The rest of them are little bit jokes. Or the last one is, at least. Okay, and then some more context down here at the bottom for some frequent derivative and antiderivative relationships. In the first one, it's asking us blank is the rate of change of work. That's power. Power is the rate of change of work. So work is the rate of change, or energy, if you want to phrase it that way, is the antiderivative of power. Surface area is the rate of change of volume. So volume is the rate of change of surface area. And marginal cost is the rate of change of cost. So cost is the antiderivative of marginal cost. Just a few other relationships between functions and their derivatives.